2, 1, recording started. Okay, so let's go to the topic in this class over here. Okay, so we are going to take a detour on the expansion chapter and take this half an hour study about very important polynomial that human has discovered so far, and that is the Legendre polynomial. I have checked Google pronunciation, and I found that in French, it is pronounced Legendre polynomial. Legendre polynomial. So it is kind of very interesting pronunciation. So I will go with this Legendre polynomial in this lecture. Again, if you have any question at all, please stop me anytime and ask a question. If you like, where is Dichen? I am seeing here Shanida Patarada, but Dichen is not. Let me click request to join. Maybe she forgot. Okay. So let me give her oh, she's here. Okay, so welcome back, Dichen. I hope you're doing fine with the mathematics.
Okay. Yes, Sajjan. So sorry, I was waiting in a different team.
Okay. Oh, are you busy? Can you attend this team?
No, Ajahn. I thought the mathematics for physics before midterm class. I was waiting there in.
I don't get your answer. So can you go or can you not stay in this meeting?
Yes, Ajahn. I was saying that by mistake. I was waiting for that before midterm mathematics class. For the class.
All right. So, well, that's okay. Okay. Before we begin, let me turn on the theme song. Okay. So we are going to be taking a detour to this material and talked about Legendre polynomial a little bit. We studied last week that this polynomial is a group of orthogonal polynomial. Orthogonal means that if you integrate them, you get 0 if they come from different order of polynomial. For example, P0 times P1, integrate, you get 0. P1 and P2, you get 0. As long as they're not the same, you always get 0. That's what orthogonal means. So why is this Legendre polynomial important? Let's talk about the universe. Almost everything. Okay, so not just this planet, but universe. Are you? Okay, that's better. Maybe Dichen is on a bus or something. Okay, let's get back to the lecture. So why is this Legendre polynomial important? Let's talk about everything, okay, in this universe, not just this planet, but the sun, the moon, and all the galaxy. What do all the things in the universe have in common? And that's just gravity and electricity. So what do all these two forces have in common? And that is 1 over r squared force law. So everything in the universe, for the most part, almost everything, obey this 1 over r squared force law. And if you think about this physics, not in terms of the force, but the potential, you can calculate potential, and that is 1 over r potential. And I hope you have seen this relationship somewhere in the undergraduate level. 1 over r squared force means 1 over r potential, for example. And the Legendre polynomial, this here, give us a way to compute this potential due to many particles and objects with shapes. So you can imagine that everything in a universe, being the electric or gravity, always obey this concept of Legendre polynomial. And that is why this polynomial is very important if you want to explain or compute anything about this universe, an object, a planet, atoms, galaxies, and so forth. And so with that motivation, let's get to the very basic of this concept of Legendre polynomial. And I am going to throw in many other concepts like multipole expansion and also what is called generating function. Okay. Now, I noticed that last week the students in you did not ask any questions at all. That is not which makes it very quiet in this lecture. So I would urge the 3 students to ask questions very often in this class. Any question at all, just ask how I am doing, why I am wearing green shirt, and so forth. Any question would do to make this lecture more lively. Okay, so suppose we have a complicated objects with 3 charges, Q1, Q2, and Q3, and we want to compute the electric potential at this point in the lower left corner of the screen. Now, I am talking about electric force here, but it might as well be applied to gravity as well, because the math is the same, is 1 over r potential for these 2 fundamental forces of the universe. So we have 3 charges in this object, and we want to compute the U, the potential at this point. Now, let's pick a center for this object. I put center in quotation here because the center we are talking about here can be any definition of center. It can be a geometrical center at the very center of the shape. It can be the center of mass. It can be any point that the person who's analyzing the problem choose to be the center. At any point will be fine for this purpose. So the charges relative to the center is given by this vector or its arrow R1, R2, and R3. And this big capital R here is the line drawn from the center of the object to the point we are trying to find the potential here. So what is this potential find over here at the lower left corner? And how do we do it? Let's see. We would just do this simple calculation of computing the distance from the charge Q1 to the point that we are trying to solve for potential. In this case, we draw this vector green over here. And if you are familiar with high school vector and physics, you can compute this green vector as a function of the capital R and the little r1. Say this one here is big R minus little r1. So that is just a simple vector subtraction. You get this arrow here. And therefore, the electric potential at this point, U is equal to K. K here is the high school constant in the electricity. Okay, just any number would be okay. And the charge Q1 divided by the distance from that charge to the point here, that is the absolute value here, means the magnitude of the vector. Okay, that is only for this Q1 charge. But we have 3 charges in the systems, and therefore we have to add all this contribution from Q2, from Q3, and so forth. Or we can use the sum to represent the total potential at this location. It is all okay. You know how to do this in high school physics already. So we have three terms here on the right-hand side because you have three particles. Now, for the real object, in the real systems, proteins, complicated object and charges, you are going to have millions and millions of charged particles here. Not just three, but millions of them. And so you have to do this million times calculation to get all the charges and all the distance from that particular charge to the point U here. And in engineering, we don't need to know the U here, just that point. We need to know the U at this point, at that point, or any other point around the object. So we have this object right here. And you need to know the potential at any point around the object. And that'll be thousands of points to compute the potential, millions of particles. So the calculation becomes very complex and very expensive, very fast. And you cannot do the actual calculation in a computer because it's just too expensive to do. If you look at all the details of all the particles in every position, it's not practical to do because it's too expensive. Okay, so can we find a way to approximate the answer? And if you have a good approximation, then it's okay for engineering applications. So let's find a way to make an approximation. The easiest way to do that is the zero order approximation. And so how do we do that? Well, we think of it as a very easy approximation. We have this object has three charges, 1, 2, and 3. Then we simply think of them as the whole object by ignoring. We are ignoring all the details of the location of the object. We ignore R1, ignore R2, ignore R3, and then think of it as a whole big object with the charge of Q1 plus Q2 plus Q3 and so forth. And therefore, in this approximation, the potential can be approximated as K, still the constant, the total charge divided by the distance from the center of the object to the point we are observing the potential. It is simple enough, and you will be surprised how many quantum mechanical calculation software uses this approximation. And in real life, in engineering application, we use this all the time. It may seem rather, stupid approximation, but it works very well. And I'll show you why it works very well in this case. Okay, so I hope so far you can follow the lecture here. So we get this final result of the U just simply Q divided by the distance from the center to the point we are trying to compute. Okay, so to use this as the real application in engineering, we need to know the error characteristics. Okay, we need to know how big the error is, and if that is too big for our application or is small enough to be okay. We need to know that. We also need to know if we can make it more accurate. So this is what we call the zero order approximation. We ignore all the R1, R2, R3. Can we make it more accurate? Let's say first order, like a little better approximation. Can we do it? And the last item is that, can we make it even exact can we change this sign from approximation to be exact? Can we do it without using all the details of R1, R2, R3, just simple average properties of the object? Can we make it exactly without any approximation? And the answer is yes, yes, and yes. And we will do that with what we call Legendre polynomial. Okay. So let's look at the basic of this approximation over here. Oh, screen is blocking the view. So the following slides will be somewhat mathematically intensive, but so I just need to prepare you for what's to come for these 2 or 3 slides in the future. But you can remember that we are talking about a big problem of the universe. And if you understand these 2 or 3 slides that's going to come in the future, if you understand them, it means that you have unlocked in your mind the inner working of the universe, the gravity, the electric charges, the quantum mechanics, all the things in the universe. Okay. So with that preparation, let's get to it. Suppose we only consider just one charge or one mass. You can use this for the gravity. It'll be mass instead of charge. So we have this one charge, and that's the center here with the cross symbol. And the little r1 is making the angle theta1 with this vector r for this example. So we can draw this exact distance from the charge q1 to the point using this vector notation, big R minus little r1, like so in the screen, on the screen. So what do we do next? The exact potential at this point, lower left corner here, is q1 divided by the exact distance. It is green line here. Okay. So let's do some manipulation of this term. The magnitude of r minus little r. Can we change the form a little bit? And I have here in this box here at the upper left corner, you see the basic high school vector. Just to remind you what's going on in the basic of high school vector. So we have here the magnitude of a vector A is just the square root of a squared. A squared is the a dot a. Very simple as that. And so therefore, if we make this analogy using a as big R minus little r, this is what we get. We get this a dot a right here. That's a dot a. Okay, one vector dot itself. If we expand them, you get r squared in the front, and the two in the back term, you have r1 squared in the rightmost here. But the term in the middle come from big R dot little r and little r dot big R. But you can swap the order of the dot product, and therefore you have here at the end 2 r dot little r. Okay, so I hope that you follow this just fine. Okay, I don't know if I'm going too fast. Let's ask I don't know Patrada here. Can you follow this math? Is okay? How you doing? Okay, thank you. I should give you an applaud every time you make a contribution to the discussions. Okay, so we are going to rewrite this denominator down here to make it little bit more complicated. So we transform big R minus little r into square root of big R squared minus 2 r dot little r, and then at the end, little r squared. Very simple. Now the dot product here can be written as the magnitude and cosine of the angle. I am going to keep this color in blue if I mention the color, the angle of the theta. So we have here 2, the length of the big R, the length of the little r, and then cosine of the angle between these two vectors, which can be any angle can be 30-degree angle, 60, any angle would be fine for this case. So we have this simple. Still, it is an exact expression. There's no approximation here, just exact. Okay. So what do we do next? We can factor out. We have this r squared here inside square root. We can take it outside over here. So therefore, inside we have what is left is 1, and then divided by r here in the middle, and divided by r squared here in the rightmost term. So I hope you can see this. You just have to factor out big R from the square root, and you get this expression. Okay. So now we are getting with a lot of symbols. There's so many variables on the screen. It becomes chunky. Okay. So to make the screen looks better, looks nicer, I can define another variable. Let's call it T1. It's defined as little r divided by big R. If I define this term, I can rewrite this square root into this nice expression. The rightmost here becomes T1 square right here, and right there, T1 square. Little r divided by r here, just 1t over here. So we have this nice looking expression. But still though, it's still an exact, not an approximation, an exact expression for the potential due to the charge Q1. It just looks different, okay. But if we look at this form we have just derived so far, you can split them into two ingredients. The first one is a simple one with the charge divided by distance of an object. This is what we want, okay, but it's very simple. But we have this extra term over here, which makes the whole thing complicated. As long as you want to be exact, we cannot omit this term. We have to keep this term to make the whole thing exact. But still, we have transformed this nice looking vector into weird, this two form here, the simple and the extra term. Okay. So what should we do next? This term here is very complex. We can't, how do we deal with this term over here? Okay. So before I show you how we can make this term go away, this extra term here, let's use an example to make it more vivid, okay, to follow the discussion better. Let's take an example that the angle theta is 80-degree angle, and therefore cosine theta in this case is 0.174, which will be colored in blue throughout the discussion. So how do we deal with this term over here? 1 over root of this guy here. So how do we do it? Let's ask someone who's going to be the Lojong. I mean, if you can imagine, if you are a person who was born 300 years ago and you would do this, and how would you do it? How would you deal with this complicated expression? You know, with the square root, with the t square and so forth. Okay, but remember the t here is very small. Why is that? Can anyone tell me why the t is very small in most application? T is the ratio. Yes.
Because greater than small r.
The t is the ratio between the little r and the big R. Why would the t be small?
Because a big R is much greater than small r.
Can you give me an example? besides the mathematics?
Like 1/1,000,000, like that.
Okay. So, for example, if I should give you an applaud over here. Okay. Thank you. Very
Thank
good.
you.
Um, so for example, if my object is my hand over here, okay, my fist over here, and you get these 3 charges or 5 charges at my nail over here. So we got 5 charges. The distance that we are observing potential will be right there, okay, very far away. The big R is very far away compared to the little r. And therefore, the t will be a very small number, okay? So we have this expression, complicated expression, and t is also very small, very small. How do we deal with this function to make it simpler, to make it nicer, but still keep a very good approximation or can be an exact too? Any idea? Just, we are waiting for the Legendre, the mathematician in this century. If you came up with this solution, the series would be named after you instead. You would have the Duchenne polynomial as opposed to Legendre polynomial. So how do we deal with this thing here? Any idea? After all, we have studied expansion last week, and you should have some idea of what is. Anyone from outside Naresuan universities, maybe you have this idea of what can you do when you have this complicated expression, and you know for sure that this little t here is very small.
Can we do binomial approximation?
Binomial, is that what you?
Like, when the t is so small, so like we can change like drop 1/2 and multiply in front of the small, like, yeah, I'm not sure.
Okay, you're almost there. The problem with your idea, which is very good as a start, is that it becomes an approximation. What we want is to have an exact expression. Also, it can be approximated, but it can also be exact. Okay, and the answer is it's very close to what was this you named it? Tasanapon. Okay, very good. The answer is that we perform Taylor expansion of that 1 square root term. So what do we get? We simply just do this power series expansion that we studied last week. We have this term here is equal to a constant a0 and a1 t1 a2 to. I have this typo here. Okay, I should change this in my slide before I save it up. Let me change it right now so I can when I give you the PowerPoint. Okay, let me change this. I need math type. Okay, I use math type for all the equation and things in Windows, which I bought it from online. It's not expensive. Okay, so we use Taylor approximation, and you have this bunch of coefficient in the power of the t. But this is not approximation. It is the exact expression. As long as you keep this power series to the right, keep it going, you have this equal sign between the left term and the right term. Okay, so still exact. I can use what I learned from last week to compute the coefficient. A1 A0, A2, A3. So let's remind you what we can do. Let's ask here. Let's ask Di Chen. Do you still remember the formula for the coefficient an in the Taylor expansion?
Excuse me, I cannot catch.
Oh, good. Questions. I love questions.
Why you use the T1 and T2 in its Taylor expansion? Because the term square root, it just only have only T1 while you use T2 square.
Oh, okay. Man, I think this is a good point. Okay. So now I was confused. The variable is T1 is already correct. Okay, so we only have a single variable T1 in the expression. Okay, very good. Thank you. I have lost. Where's my PowerPoint? Okay, let me take this second break to load my my file. Okay, very good. Okay, what's your name? Ron. Okay.
You just call me Ron. Yeah, Ron.
Okay.
Ron.
Thank you. I almost made a very serious mistake. Okay, so think of the T1 as X. So we only have a single variable. Okay, therefore we having T1 here is already correct. Okay, so thank you. So, Di Chen, what is the formula for computing an?
An is equal to?
Yes.
1 over n factorial. Was it?
Okay.
N factorial.
And then?
Differentiation dnf.
Okay.
X.
The nth order derivative of x
f
of the f. Okay,
f,
then evaluate it at the center. In this case,
x equal to 0.
0. Okay, very good. Thank you. So we can do this, except that for this example, the f of x is this expression, and it is f of t as opposed to the x that we have in the iPad screen. So I can do this using the concept of expansion, and I get this coefficient. A0 is number 1, A1 is just that number here, and A2 and A3 so forth. And still we get exact expression for the left-hand side. No approximation here, an exact expression. So what do we do next? Okay, before we go on to see the example of how the error characteristic will be, let me show you just an introduction of how we can make it better. We talked about zero order approximation, and by replacing the whole exact expression by just A0, which is number 1 in this case. A0 is 1. So we approximate this whole thing by just number 1. Okay, very bad approximation, but it works. Okay, we can go to the next order, the first order approximation. We keep this term also, A1 T1, which will be this number times T1. That is first order approximation. We can keep on going and going. We're going to get better and better expression. Okay, so we have that concept. If we use this zero order approximation, this whole thing is number 1. So we put this number 1 back into the big expression. What do we get? We get this u is approximated by this coefficient times number 1 over here, and that is the monopole approximation. Okay, because we think of it as just one big charge of the whole object. Here we add the second charge, the third charge, and so forth. We get this expression as the simple charge of the whole object, like so. Okay, so that is a zero order approximation. We are going to talk about the first order later on after the example. Okay, Now, we have this Taylor series approximation or expansion. We can choose it to be approximation by keeping only one term and two terms, or we can make it exact by keeping all the terms. Okay, it is very systematic way of doing it. Okay, let's look at an example. Okay, yes.
I'm sorry for interrupting you.
Yes, very good.
We have big I mean with the big capital letter one.
Yes.
Is for the distance to center of mass, right? And for
distance. Okay.
from the formula, we have we remember that U equal to KQ over R, and you say R can be the distance to any center, that
Right.
any definition of center, right?
That's right.
I
That's
just
right.
think that the formula that we remember, what is the most definition that they use?
Okay. So
Or in what different? I'm not sure.
Okay. Thank you. Thank you. Let me give you an applause over there. Okay. So Chanidapa is concerned with the choice of the center that we are talking about now. As far as the mathematics goes, you can choose any point to be the center. It does not change the structure of the mathematics. But the choice of these center will give you better approximation or worse approximation depending on the choice of your center. Sometimes we choose this to be the center of the object. Like if you have a sphere, that will be the center of the sphere. Or we can choose to be the center of mass, but most of the time we use a center of electric charge. Okay. I am not sure if you know what that means. It's very similar to the center of mass, but it's a center. It's called the center of electric charge. Let me go to the iPad screen to show you this a little bit about the center that they use in research or in the software. Okay. For example, if you remember in your classical mechanics here, we have the center of mass, xcm, okay, is equal to, by definition, and you can choose this, and it's a summation of the mass mi of that particle times the position of that particle in x direction. And then you have this here, I here. That's the center of mass, okay? But you have to divide by the whole big mass over there too. Okay, that is mass, the center of mass. The center of charge is the same concept. You can choose this x, and I don't know if they call that CC. Maybe I'm making this up. I don't know how they call it, but you can do the same thing as sum of the qi xi of that particular chart and divided by the capital Q, the total chart of the object. That is one choice of the center, and this choice will make the whole thing most accurate for this approximation. Okay, but in detail, I can't go that deep, okay, because we don't have much time. Okay, I hope you are happy with the answers for now. Are you happy with the answer? Okay.
Yes. Thank
Okay.
you.
So we can choose any center you want, but it will give you different degree of good or bad approximation. So by now you may ask, I have promised you about the Legendre polynomial. So where is it? And I talked about this special thing that's called generating function. Where is it? And also this expansion. It turns out that you have seen them all in the previous lecture, but I just haven't told you or the name of the expansion. But practically, if you understand how we do this expansion, you understood Legendre polynomial. Okay. I'll give you the formal definition in a few slides. Let's look at the example first, okay? I need to have a sip of water here to see how the error behave in this monopole approximation. Suppose we have very simple 3 charges system, like here, and the distance from the center here is 1 unit. Now I am very lazy to use the constant k and the q and all things here, so I'm going to make it very simple for me to define the charge to be exactly 1 unit, and the distance is also 1 unit here to make my life a lot better. So with that 3 charges, I can compute the exact potential in this way. I can draw this line here using Pythagoras theorem from that charge to the point, like so, and therefore the distance will be root of r squared plus 1 for that top triangle. For the bottom one here is the same. For the middle line here, you have this r plus 1. Okay, that's the distance from that charge q2 to the point that we are looking at the potential. So that is the exact expression for the potential. It depends on big R. If you go far away and far away and far away, the U will be different. What about this simple monopole approximation? You simply just have to compute the total charge. 1 plus 1 plus 1 is 3, divided by the distance from the center, in this case, only big R there, okay? So of course, this is an approximation, but let's look at the error profile of this approximation, okay? On the left graph, I am plotting here is the distance big R from almost 0 to 20 unit, okay? In the vertical axis, I am plotting the potential, the exact is blue, and the orange is the monopole approximation. As you can see there, if you go farther and farther away, the two becomes converged to almost the same answer. Like you add this 10 unit here of distance, almost the same value for this here, and onward you get the same value, okay? But if little r is if big R is small, you have a very bad approximation. If you compute the error, you subtract the monopole from the exact value, you get this red curve over here, okay? This is the error profile. Again, the vertical is the error, and the horizontal is the distance of big R. And I am plotting in log scale over here. You see here, when R is 10, you have 0.001, okay, very small. And as you go farther away in the R axis, the error gets very small, okay. So this is the error profile of this monopole approximation. But what is the mathematical expression for this error? You know, it's is it 1 over r, 1 over r squared? What is the profile of this error here? Okay, let's look at the profile. On the left here is the same graph as before. On the right, I am plotting 3 functions to compare the function of 1 over r with the cross, 1 over r squared as a circle dot, and r cubed is triangle dot. And you can see that here the 1 over r squared agree perfectly with the error of the monopole approximation here. So therefore, we conclude with this example, only with this example, that the error goes like 1 over r squared. Now, what does it mean when the error goes over like 1 over r squared? It means if the distance is 10 times bigger, the error is 100th time smaller, okay? 10 squared is 100. If the distance is 5 times bigger, the error will be 25 times smaller. Okay, in this case, it's kind of very good. Okay, but the question is it only true for this example and not in general case? And can we make it better, an approximation? Can we have a better or less error? Okay, so to analyze this, let's go back to the basic of the expansion. Recall that we have this exact expression into two groups, the simple form multiplied by this extra term over here, and we expand this into exact Taylor expansion, like so. Zero order, we keep only the A0. Here we keep the A1, T1 also. We call it first approximation. Now, suppose we only keep this monopole term over here. What does it mean? It means that we ignore this first term over here and the later onward, but this term becomes the leading error of the approximation. Okay, the leading error. Let's look at this leading error. Okay, because T1 by definition is little r divided by big R. So we multiply T1 back into the front, you get R squared. You get R 2 times, one R from the front here, and another R from the T definition. Therefore, the leading term, which we ignore in this case, is the error goes by 1 over R squared in this case. Okay, so this turned out to be a general properties of this expression, of this approximation, not just this example. Okay, so we call that 1 over R squared error. Now the Legendre polynomial. Let's look at the formal definition of this polynomial. So we have changed the angle to be more general. For example, we used previously this angle, and that cosine theta 1 is 0.174 in blue color, and we get that expression. However, in general, theta 1 can be any angle, and therefore we can define another variable to make it more convenient. We call that x. X is cosine theta 1, and therefore the x can change from all the range from where to where. Let's ask us questions as to make it more lively. So can anyone tell me the range of x if theta 1 can be any angle? If I define x as cosine theta 1, what will be the range of the x variable? Anyone? But
the value of yeah
wrong.
-1 to
Okay.
1. Yeah.
Very good. So we just go from -1 to +1. Okay, of my x variable. So I can just, with that notation, with this definition, I can write this form in a very general way. Instead of using 0.174, I use the x instead over here. So I can expand them into Taylor expansion, the zero order, first order, and all the order here on the right-hand side. I can work out all that coefficient using my Dichen's expression. Where's my Dichen's expression? Okay, this is the Dichen's expression. Okay, and I get this over here, and that is precisely what the Legendre polynomial is. It is a Taylor expansion of the 1 over R potential of the fundamental forces of the universe, the gravity and the electric forces. So the zero order Legendre polynomial is A0, it's just 1. The first order Legendre polynomial is x because A1 is x. That's the second order and the third order and so forth. So that is what Legendre polynomial is. Very simple. What about this function here that my cursor is pointing here? That is the beginning of the function. Okay, we use this function, expand them, you get Legendre polynomial. That function has a special name. We call them generating function for Legendre polynomial. Generating function. It is a function that generates series of many functions afterward. Okay. What about this? What about each term of this expansion? We call that the multipole expansion. The first term is the monopole expansion. The second term is dipole, and third term is quadrupole, and all the other pole there in the series. We call this in general multipole expansion. Okay, so let's take a break from this PowerPoint and go see this Legendre polynomial in the World Wide Web, just to show you if you want to search more about this thing, what can you do? Okay, let's go to Wikipedia. It's not really reliable source of information, but it's a good start. If you would ask what is the source or the of my math information, I would use this. I have this big book. It's called CRC in mathematical formula. Okay, mathematics. Okay, over there. CRC, what? Mathematical formulae for me. There you go. Okay, so you should go find what this is. There's a book, but I have this book with me all the time in my office. It's a big, thick book. It's called CRC Standard of something and something. Okay, very expensive, but it's worth it. There should be no error in this book. But in the beginning, you can just look at the Wikipedia over here. If I scroll down the windows, I can see this definition of Legendre polynomial over there, over here. If you read this equation 2 and you understand right away what it means, well, you have understood my lecture very well. It's just that here, that Legendre polynomial comes from expansion of this generating function over here. You expand this and you get a series, and the coefficient of this series are the Legendre polynomial. Okay, so I hope that thus far you understand this here. What about the generating function? There are many kinds, all kinds of generating function for many purposes and application. If you go to this Wikipedia website on generating function, you scroll down here, you look at this here, you see the very simple way I use this is over here, over there. So you have seen this somewhere, this proof over here. I'm sorry. Okay, there. This is called geometric series. Now on the right is the generating function of the expansion on the left. And that's how you prove this identity in mathematics. Let me put that in the language that you have seen in high school. Okay, in high school mathematics, I believe that we use a symbol R. For example, my teacher would ask me, what is this series? 1 plus 1/2 plus 1/2 square plus 1/2 and then to the third power and so forth is equal to what? You know, you keep adding them to infinity. Now, when I was a child, I was very surprised by this identity. Very surprising. How can you keep adding all the term and know the answer at the end? It seemed to be very impossible task to add so many terms but get the answer. But that turned out to be what value? Anyone? Anyone knows the answer? I can yes.
2.
2. Very good. So I can do this r squared and then r cubed. That's 1 over 1 minus r. Okay, that's the answer. We call this geometrical theory. But how do you prove this? How do you prove that this identity is true? Any idea? Any idea? I believe I just told you, but
come out to the series and then minus the next equation with the previous equation.
Very good. So so Mr. Ron is on fire today. So we simply take this function of f use any f of r is equal to 1 over 1 minus r, and we expand them into power series, expand them, and you will see that the coefficient will always be 1 here, 1 here, 1 here, and 1 here. All the term here will always have the 1 coefficient, and therefore this expression is exact. Okay, that is one example of what we call generating function. This function generates the list of many other functions. Now there are many kinds of generating function in modern mathematics, and you can look at them. Many series, this one here, and that one here, and so forth. Okay, all right. So let's get back to the end of the Legendre polynomial, which is the multipole expansion. Okay, previously we have studied expansion, and I told you that many things can be broken into pieces, like my hand. I can break my hand into nails and bones and palm and so forth. The same thing with charges. If I have an object on the left, it looks very complicated with many charges on the object, but I can expand them, or I can break it into many pieces, which we call the monopole piece, as is one charge, or the dipole piece, or the quadrupole piece, and so forth. And each will have different mixture. Maybe for this example, you have 70% of the monopole and so forth. So this is what we call multipole expansion. Everything, every charges, every mass and gravity can always be broken into pieces, and each piece is a monopole, only one charge, plus the dipole, the plus and minus, and quadrupole, the 4 charges group, and so forth. That is what we call expansion. Okay. For example, if you go to quantum mechanics, you can use quantum mechanics to study many of the small objects like molecules, atoms, and so forth. For example, water are the most abundant molecules on Earth, maybe in life itself. So this water molecules has 0% monopole because the charge is 0, total, neutral. But it has what we call dipole moment, because you have the top here is more negative than the bottom. The bottom is more positive. And therefore, you have this dipole moment of this object with 0 monopole. When I say dipole, I mean it's ideal. Ideal means the charge, the plus and the minus, is very close to each other, almost touching. In ideal case, almost touching. Okay, there's no distance between the plus and the minus. That's the ideal dipole. Okay, I can't see myself. It's kind of hard. So let's look at the before we go into the research application, let's look at the interaction between objects. Okay, we have star, galaxies, or atoms and molecules, gravity or electricity. You have an object, 2 of them on the left with the charges, on the right also with the charges, with different charges configuration. If you want to compute the forces interaction between these 2, what do? Well, you do this here is very complicated because you have so many details. On the left, you may have millions of charges. On the right, you have another millions of charges. So you cannot do it directly. What do? You simply split this whole thing into a series of monopole, dipole, quadrupole, and so forth. So you have expanded this object on the left into a simpler poles of electric charge. Okay. The same thing is done with the object on the right here. You may have different mixture of each here, depending on the object. And now you can let these two interact over here. For example, it turns out because of the mathematics of Legendre polynomial, if you remember that these polynomials are orthogonal, it means that if you have the two different type of order, you multiply them, you get zero integration. Because of that mathematics, it becomes this physics law that only the same kind of pole will interact. Monopole and monopole interact only. Monopole does not interact with dipole, okay? Because of that orthogonality of the Legendre polynomial. You can look at this in the simple physics. For example, if I have this is a dipole, okay, I have two fingers, that is the top one is positive and the bottom one is negative. So we have this a dipole here, okay, and the monopole is right here, okay. Based on that slide, this monopole does not interact with the dipole, okay. Anybody knows why? It does not see each other. If you have a monopole here and an ideal dipole over here, they don't interact. They don't see each other at all. Why is that, do you think? This one, the top one is positive and the bottom one is negative. And this monopole here may be +5 or something. Any idea why monopole does not interact with ideal dipole? Anyone? Yes.
Maybe
yes.
They don't have any free charge. The dipole must have equalized one another, and they may not have free charge too.
Okay, very good. The concept is the forces, they balance out, they cancel each other. The dipole here, you have positive and another equally negative charge. And therefore, let's look at this charge +5 over here. +5 and the plus charge at the top and the minus here. And therefore, they cancel each other. And at the end, you have a zero interaction, okay? Ideal dipole, okay? Ideal dipole. So come back to here, you will see that monopole interact with monopole and dipole interact or attract to another dipole and not other different kinds of poles. This Q here and Q there only interact with each other, okay? So what would be the application before we look? I have this here that in biology and in nature, they use this concept of the independent of the poles to do wonderful things in life and in biology. I have this article in research here in PNAS, very good journal, by the way, from the American Academy of Science. It talked about how the protein can capture molecules, small molecules, we call them ligand. Ligand is the technical term of small molecules. So imagine that you are breathing in something. So let's see me here. I'm seeing, for example, you are breathing in, okay, O2 inside, and then you breathe out CO2 outside, okay? And the internal mechanism is that your blood vessel, your blood blood cell has a protein called hemoglobin, and this protein then I need to find myself okay. For example, this here is my CO2 or my O2 molecule, this black mouse here, and my hand is the protein hemoglobin. So this hemoglobin has to capture O2 right there and capture O2 and then take this O2, travel along the blood vessels and so forth. So how does this protein knows that this molecule is O2 or CO2 and not the water molecules? Remember, our body is made of water for the most part. So you have a lot of water inside the body. But somehow this protein does not capture water. It only captures O2, the hemoglobin, and then take it away and then flow through the blood vessel. So the question is, how do proteins selectively capture O2 or CO2 and not the water molecule? Any idea? Um, any idea how you would do that? If you, I guess this concept will be most beneficial to Miss Shanidapa because she is studying protein and ligand binding interaction. Am I correct?
Yes, but I consider just the size of it.
Okay, so
So I'm not
how
sure
many?
about how specific that they why they
Was
not capture other.
okay, so you know a little bit about protein. Can you tell the audience um, what is important in the protein? What is the active site in the protein? Okay, that's the question. Can you tell us about what the active site means in the for the protein?
Okay, maybe I'm not all correct. You can recorrect me. As I know, we have protein. Protein can be any molecule, carbohydrate or
Uh-huh.
other. And then on the protein, they will have binding site,
Okay,
and that binding site will interact with ligand.
okay,
And binding site will really specific. It's like it have a type of it. If the
okay,
ligand is not that type, the protein will not catch it.
okay. So let me I always forget this. Okay, thank you. So a protein is a machine of life. Okay, in biochemistry, you have this protein. So a protein is a huge body of biology, and it has a structure just like building, and the building has inside there the center of command or an active site. So maybe this protein is this big and the active site is that small, okay, inside the protein. And this one here is functioning as the capturing uh, of the O2. That's the active site. So come back to the questions of how do protein selectively capture only O2 and CO2 and not the water molecule? And the answer is this. Okay, so this is the active site from this paper. It shows you the metal. In here we have manganese center over here. The answer is that we, or biology, or the evolution, it designs the active site such that it has a very strong quadruple moment over here at the active site. Why? Because there's a metal or manganese here at the active site. And metals always have this d orbital in quantum mechanics. I'm showing here the shape of the orbital for the manganese or the metal in general. We have this d orbital. Now this is a shape of the quadruple moment. So the active site has a very strong quadruple moment. And therefore, this active site does not interact with water. Why? Why is that? Any answer from let's say Patharada, maybe you have an idea. If the active site has very strong quadrupole moment from the d electron, why is that this active site does not interact or does not attract or pull in the water? Is there something wrong with water? Yes?
ไม่รู้ได้ไหมคะ ว่าทำ
Oh,
ไมมันไม่ชนกัน
it's okay. I see. I can still give you an applause. Okay. Okay. Now I can ask another questions. Okay. So previously we talked about water molecule, right? So water molecules, does water molecule have a monopole? Yes or no? Let's ask
Dipole.
No, they
let's ask Patrada here. Do water molecules have monopole?
ใช่
Yes, yes or no?
yes
What is the total charge of water molecule? Let's rephrase that question in this way. What is the total charge of the water molecule?
3
Water molecule.
H2O
That so the number of atoms, you have 3 atoms. That's correct.
yes
What about the charges?
the charge I think
ขนาดของประจุสุทธิของโมเลกุลน้ำมีค่าเป็นเท่าไหร่ มันมีประจุหรือเปล่ามันมีออกซิเจนถูกไหมครับ
ค่ะ
แล้วมันก็มีไฮโดรเจนแสดงว่ามันมีอยู่10โปรตอนถูกไหมมีอยู่10โปรตอน8มาจากออกซิเจนแล้วก็2มาจากไฮโดรเจนใช่ไหมครับมี10โปรตอนแล้วมันมีอยู่กี่อิเล็กตรอน
มีอยู่3ไหมคะยังไม่ใช่4มีอยู่5อิเล็กตรอนนะคะสมมติว่ามีอย่างละ10นะคะ
มีอยู่10อิเล็กตรอนถูกไหมครับแสดงว่าประจุจากโปรตอนกับอิเล็กตรอนมันหักล้างกันมันจึงไม่มีประจุสุทธิใช่ไหมครับ and so the water molecule do not have monopole at all, 0. Okay, what about dipole? มันมี dipole หรือเปล่าในโมเลกุลของน้ำ
ที่มี2ขั้ว
มันมี2ขั้วใช่ไหมครับเป็นโมเลกุลที่มีขั้วลบข้างหนึ่งตรงฝั่งของออกซิเจนถูกไหมครับแล้วก็ขั้วบวกทางฝั่งไฮโดรเจนแสดงว่าน้ำเนี่ยมันเป็นโมเลกุลแบบ dipole. The water molecules have dipole moment. That's why. So let me give you an example. Okay, and that's why the metal center does not interact with water molecule, because water is a dipole, but the center is quadrupole. And if you go back to the previous slide about the orthogonal of the Legendre function over there, you see that the only quadrupole interact with quadrupole themselves and not the dipole, not monopole, and vice versa. And that's how the active site, because of the evolution of the biology, only selectively capture carbon dioxide or oxygen molecule, because these two molecules are quadrupole molecules. Okay, they have 0 charge, they have no dipole, but they have very big quadrupole moment for O2 and CO2. Okay, so I hope you see that we found application of Legendre polynomial not only in physics but also in all kinds of science, including the biology and chemistry as well. I guess that will be the end of the lecture. Maybe you have a comments and the question before we get back to the expansion after this little break that we are going to take about 10-15 minutes. Any question at all so far? So we have ended the Legendre polynomial. Okay. No, I'm very happy with participation from the students. มีความสุขมากกับคำถามต่างๆนะครับถ้าคุณที่คุณแชร์นะครับแชร์คำตอบต่างๆไม่เป็นต้องถูกต้องผิดนะครับแต่มันมีผลที่จะทำให้บทสนทนาแล้วก็เลคเชอร์มีความสนุกสนานนะครับอาจารย์ค่ะ
อาจารย์
yes
คือว่าหนูจะถามโปรตีนกับลิแกนนี่แหละค่ะเพราะว่าเผื่องานหนูคือว่าถ้าสมมติว่ามันเป็นแบบมันจะต้องเป็นแบบเดียวกันใช่ไหมคะแสดงว่าถ้าสมมติว่าโปรตีนนะคะมันเป็นรูปแบบอื่นๆมันก็จะสามารถจับน้ำได้เหมือนกันมันมีใช่ไหมคะ
มีครับ
แสดงว่ามันอยู่กับอาจจะเป็นพื้นที่หรือว่าแบบว่าหนูจะเรียกว่าตรงอะไรเดียวหน้าที่ของโปรตีนชนิดนั้น
ใช่ครับโปรตีนมันก็จะมีหน้าที่ต่างๆso Miss Chanidapa is asking whether or not you have other kinds of protein that can interact with water. Okay, so the answer is yes. It depends on what kind of proteins and what role they play in biology. I remember that there was this Nobel Prize in physics or biology that given to this guy that explained water channel protein. Let me go to the Google and type in, and you want to see this is the special protein that acts as a pump of water in and out of the cell. Water channel, and then protein. Nobel Prize in physics. Okay, where is it? In chemistry. Okay, in chemistry, 2003. You should try to go find it and read or look at the video. So this is the Nobel Prize winning research on how cell control the water in and out of the cell. Okay, so you have this protein, it has a hole, and the water molecules can go in and out, but there's a pump that selects only the water. Okay, so the cell and life is a very highly controlled system. It cannot just let anything in and out. It has very good selective mechanism. You want to let only the salt in or the water in or metals center in. You have all kinds of protein that select the material in and out of the cell, and that depends on the design of the evolution. Okay, very good. So in here you have a bunch of network of dipole that control the channel of the water. Okay, thank you.
อาจารย์คะหน้า17
yes
ค่ะที่บอกว่า D shape นี่คือหมายถึงของอะไรนะคะแล้วแบบมันต่างจากของไฮโดรเจนอะตอมที่เป็น D shape ยังไงอะ
Oh, okay. It's the same, but for hydrogen there is no D electron. There's only one S electron in hydrogen because the number of electrons is too small. You only have one. But for metal, the orbital keeps adding. You have this S and then P, right? SP, and then the D orbital. This is the shape of the D electron. And because of this shape, this flower shape, it is the same as the quadrupole charge configuration. And that D electron will produce quadrupole moment in the molecule. Okay. And you can use quantum mechanical software to compute how much percentage of the mixture you have for molecule. You can use Siam quantum programs, any or Gaussian program to perform quantum calculation, and then it will give you the series of expansion, monopole, how many percentage, dipole, how many percentage, and so forth. Okay, so the answer is the metal has d electrons because there are many electrons, including the d orbital, but hydrogen does not have d because there's only one electron, one s in the hydrogen. Okay, I hope I answered your question. Is that, are you satisfied with the answer that I gave?
อาจารย์คะหลังๆ
Yes.
ที่อธิบายอิงยาวๆช่วยเสริมซับไทยให้หน่อยได้ไหมคะ
โอเคขอบคุณครับ so ตรงไหนครับตรงไหนผมก็รอให้คุณผมก็รอให้คุณด่าอยู่ว่าพูดภาษาอังกฤษเยอะเกินไปบางทีผมมันนะครับนานมาแล้วที่ผมได้ถ้าผมจะมันเกินไปตรงช่วงไหนครับเอาเป็นว่า so DJ let me take a break a little bit with the English session. I hope you're okay with that, and take this brief moment about the Thai version, just brief moment. อันนี้เราก็ดูพวกmultiple expansion นะครับว่าประจุถ้ามันกระจายตัวอยู่เป็นรูปร่างแปลกๆมันสามารถจะมองว่ามันสามารถกระจายได้เป็นชิ้นส่วนย่อยๆนะครับก็คือมองเฉพาะในแง่ของประจุเดี่ยวๆโดดๆเรียกเป็นโมโนโพลหรือเป็นไดโพลหรือเป็นควอดรูปโพลนะครับอันนี้คือการมองในอีกแบบหนึ่งเป็นส่วนผสมนะครับซึ่งเราสามารถที่จะหาได้ว่ามันมีค่าเป็นกี่เปอร์เซ็นต์เนาะยกตัวอย่างเช่นถ้าเป็นโมเลกุลของน้ำเนี่ยมันก็จะไม่มีโมโนโพลเพราะว่ามันประจุ net charge เป็น0แต่ว่ามันจะมีไดโพลเพราะว่ามันมีความไม่สม่ำเสมอของประจุนะครับประจุลบอยู่ด้านบนบวกด้านล่างก็จะเกิดเป็นไดโพลขึ้นนะครับแล้วก็ไดโพลเราบอกว่าเป็นไดโพลคือต้องเป็นไอเดียลไดโพลก็คือว่าระยะห่างระหว่างบวกลบเนี่ยต้องเป็น0นะครับเพราะเป็นไอเดียลไดโพลนะแล้วก็ด้วยสมบัติทางคณิตศาสตร์ของพระคุณนามเลอจองเนี่ยมันทำให้โมโนโพลกับโมโนโพลเนี่ยมันผลักหรือดูดกันแค่นั้นเองนะครับมันจะไม่อินเตอร์แอคกับพวกอื่นๆนะครับเพราะมันจะเป็นความเป็นออร์โตกอนอลซึ่งกันและกันอยู่นะครับทำให้มีประโยชน์มากในการออกแบบนะครับวิวัฒนาการของสิ่งมีชีวิตยกตัวอย่างเช่นไอตัวโปรตีนเนี่ยนะครับมันสามารถที่จะเลือกเฉพาะO2 ได้ยังไงนะครับก็ในเมื่ออยู่ในสิ่งแวดล้อมเนี่ยมีทั้งน้ำทั้งเกลือทั้งทุกอย่างเต็มไปหมดเลยทำไมมันเลือกจับเฉพาะ O2 กับ CO2 นะครับเหตุผลก็คือว่ามันได้ออกแบบขึ้นมาให้ตรงกลางของมันเนี่ยหรือว่า active site เนี่ยมีเฉพาะ quadrupole moment นะครับซึ่งมันต้องเป็นรูปร่างแบบเป็นกลีบดอกไม้แบบนี้นะครับแล้วมันมาจากอะตอมของโลหะเป็นส่วนใหญ่นะครับเพราะว่ามันมีอิเล็กตรอนปรากฏอยู่ทำให้มันจะดึงดูดเฉพาะโมเลกุลที่มีควอดรูโพลโมเมนตัมเองกับแบบนี้นะครับแต่ว่าน้ำเนี่ยมันเป็นไดโพลมันจึงไม่ดูดกันกับพวกโปรตีนเหล่านี้นะครับแล้วก็ธนิดาภาก็เลยถามว่ามีโปรตีนอื่นอีกไหมที่มันดูดไดโพลได้ก็คือมีที่ดูดน้ำนะครับโมตอบว่าใช่นะครับเพราะว่ามันเป็นเครื่องจักรของสิ่งมีชีวิตในการที่จะควบคุมการกินการขับถ่ายของเซลล์นะครับทุกๆอย่างเช่นรางวัลโนเบลปีนี้นะปี 2003 เนี่ยก็คือเขาสามารถที่จะถอดรหัสกลไกการทำงานของ water channel นะครับของเซลล์ได้นะครับตัวนี้เป็นตัวปั๊มที่คอยเลือกเฉพาะโมเลกุลน้ำให้ผ่านได้เท่านั้นเองนะครับซึ่งคุณดูคิดว่าเซลล์มันมีการเลือกยังไงวะเพราะว่ามันไม่มีคนที่จะมาคอยแยกแยะว่าเป็นโมเลกุลไหนใช่ไหมครับมันไม่มีบัตร ID ในการที่จะเช็คมันต้องใช้ฟิสิกส์ในการแยกนะครับว่าให้เฉพาะน้ำผ่านฟิสิกส์นั่นก็คือว่าใช้ไดโพลของน้ำนั่นเองนะครับเป็นตัวสกรีนเป็นตัวกรองนะครับถ้าเป็นพวกไอออนเช่นเกลือโซเดียมมามันก็ผ่านไม่ได้เพราะมันเป็นประจุบวกอย่างเดียวนะเช่นนี้เป็นต้นครับก็ so I hope you are happy with the introduction to Legendre polynomial and how we use that in the application like biology. If you have any other questions, then you can send me email or put that.
สอบถามนิดนึงครับไอ้ตรงเนี้ย
Yes,
ไอ้ตรง
please.
ที่ว่าเป็น interaction เนี่ยก็คือที่เราแบ่งเป็นกลุ่มอย่างเงี้ยแล้วคือไอ้โมโนโพลไดโพลควอดรูโพลแล้วต่อไปมันจะเป็นอะไรฮะคือมันจะเป็
ต่
น
อไปใน
มันจะเป็นแปดขั้วหรือเปล่าหรือไงอันนี้คือ1ขั้ว2ขั้ว4ขั้วต่อไปมันจะเป็น8ขั้วไหมหรือไงเพราะว่าอย่างอันเนี้ยมันเป็น 20% 70% แล้วก็ 4% มันยังไม่ครบ 100% แต่ว่าไอ้ที่เหลือเนี่ยมันจะเป็นอะไรฮะ
มันมีต่อไปอีกครับผมจงใจใส่ให้มันไม่ครบร้อยเพราะว่าจะได้รู้ว่ามันมีต่อไปอีกครับเดี๋ยวผมจะพาไปดู multiple expansion นะครับ multiple expansion ซึ่งเป็นอีก so Mr. Ron is asking in this series of multiple expansion we have monopole, dipole, quadrupole. What is next in the series? What is the number of poles? Okay, so we have this huge expansion over there. Okay, so we have this monopole term, dipole term, quadrupole term. I am not familiar with the next term. I forgot what the Q is quadruple. What is the next pole? I guess 1, 4, 5, 3. Could be octupole. อาจจะเป็น8นะครับแต่ว่าคือมันเป็น2ยกกำลัง2ได้4แล้วก็4คูณ2ต่อไปอีก8แต่ว่าผมไม่มั่นใจว่ามันเป็นเท่าไหร่นะครับคือมันไม่เคยมีคนใช้นะครับเพราะมันจะสูงเกินไปแล้วก็มันยิ่งดุ้งไปใหญ่นะครับประมาณนี้
ใช่เพราะเห็นเปอร์เซ็นต์มันไม่ครบไงฮะก็เลยอยากจะรู้ว่าต่อไปมันน่าจะเป็น8ใช่ไหมหรือว่าเปอร์เซ็นต์ไม่ครบก็ช่างมันเลยฮะแล้วตรงเนี้ยเปอร์เซ็นต์ไม่ครบ100ก็
ผม
ช่าง
จ
มั
ง
น
ใจใส่ให้ไม่ครบจะได้รู้ว่ามันมีอื่นๆต่อไปอีกนะครับ
อื่นต่อนี่คือไม่แน่ใจว่าแต่น่าจะเป็น8ใช่ไหมฮะ
ครับผมโอเคมันมีซีรีส์เพราะมันเป็นซีรีส์ครับเวลาที่เราใช้โปรแกรมคำนวณมันก็จะบอกเราว่ามันมีผสมเป็นส่วนใหญ่เท่าไหร่ประมาณนี้ครับโอเค
ครับ
so thank you for listening to the lecture we'll get back to the expansion in about 15 minutes we'll get back after break I hope okay before we have a break are you happy with the new screen configuration
Yes.
Yes.
Yes, sir.
Okay thank you I'll see you in about 10 minutes 14:40 I'll come back I can't leave that long because my screen's gonna go into sleep mode all right I'll see you in 10 minutes there you go เหลือเวลาคุยเล่นอีก5 นาทีก็เปลี่ยนบรรยากาศนะครับรู้สึกสบายแล้วก็พูดมันมากครับที่ได้เลคเชอร์เป็นภาษาอังกฤษนะครับคำศัพท์เทคนิคหลายอย่างหรือแม้กระทั่งเวลาคิดบางทีผมก็คิดเป็นภาษาอังกฤษน่าจะฝันเป็นภาษาอังกฤษเพราะว่าถ้าไปอยู่นานแล้วมันก็จะหลีกเลี่ยงไม่ได้ที่อยู่ในโหมดของการคิดแบบนั้นแล้วก็ถ้าพูดออกมาเป็นภาษาอังกฤษมันก็จะสื่อสารได้ไม่ขัดนะครับมันไม่ต้องแบบแปลเป็นไทยอีกทีนึงบางทีผมก็จะงงโอเคก็คุณพัทรดาเปิด
จะบอกว่าเราต้องฟังจนกว่าจะฝันเป็นภาษาอังกฤษเหรอคะอาจารย์
อ๋อใช่ก็มันก็น่าจะเป็นประสบการณ์ที่แชร์กันตอนที่ไปเรียนที่ต่างประเทศนะครับพอเราอยู่ไปได้สักพักหนึ่งประมาณสัก6 เดือนเราก็จะเริ่มฝันเป็นภาษาอังกฤษเพราะว่าความฝันนี่ก็คือจิตใต้สำนึกของเรามันก็คิดขึ้นมาใช่ไหมครับถ้าเกิดเราไม่ต้องแปลแล้วในฝันแต่จิตของเราคิดออกมาเป็นภาษาอังกฤษเลยก็แสดงว่าเราได้ใช้มันเป็นส่วนหนึ่งของความคิดไปแล้วไม่ต้องมีการแปลผ่านทางทีนี้พอเวลาไปเรียนหนังสือไปเข้าใจไปแอบสอบพวกความรู้ต่างๆมันก็จะแอบสอบเป็นภาษาอังกฤษแล้วมันก็จะถูกบันทึกเป็นภาษาอังกฤษไปในตัวพวกวิชาที่เราเรียนมาทีนี้พอจะมาถ่ายทอดบางทีมันก็ลำบากหน่อยถ้าเกิดต้องมาแปลเป็นไทยแล้วก็นึกว่าจะพูดยังไงวะอะไรประมาณนี้นะครับแต่ว่ามาอยู่ไทยนานก็จะค่อยๆกลับคืนมานะครับเป็นธรรมดานะครับของโลกผมคิดว่าแรกๆคุณก็ในเลคเชอร์แรกที่คุณฟังเลคเชอร์เป็นภาษาอังกฤษมันก็จะฟังยากหน่อยนะครับแต่ผมเดาว่าอันนี้คือประสบการณ์ที่สอบถามนักเรียนมาหลายรุ่นนะครับพอคุณเริ่มคุ้นแล้วมันก็จะง่ายขึ้นนะครับแรกๆมันก็จะรู้สึกมีความไม่สะดวกรู้สึกมันติดขัดอยู่นิดนึงเวลาฟังนะครับไม่รู้ว่าคุณชนิดาพารู้สึกว่าฟังได้ง่ายขึ้นในเลคเชอร์ที่2หรือเปล่า
ค่ะก็อาจารย์บอกว่าพูดแล้วฟังง่ายอยู่แล้วค่ะ
โอเคผมเห็นด้วยคุณดุย1994นี่คุณมาจากจังหวัดไหน
ครับผมอยู่ที่ญี่ปุ่น
ไม่เสียงไว้แทรก
นะครับผมขออนุญาตปิดไมโครโฟนเสียงลมแทรกคุณกำลังขับมอเตอร์ไซค์อยู่นะครับ
เปล่าครับผมนั่งตรงหน้าต่างครับ
มาจากจังหวัดไหนครับ
อ๋อผมอยู่ญี่ปุ่นครับ
เอาอยู่ญี่ปุ่น โอ้มีความเป็น international นะครับก็คุณต้องขอบคุณคุณดูอีก1994ที่อุตส่าห์มาอยู่ร่วมกันจนถึงเลคเชอร์ที่2นะครับจำนวนของแฟนพันธุ์แท้แมทฟิสิกส์ก็จะลดลงไปเรื่อยๆนะครับเป็นธรรมดาของโลกหรือเขาจะมาฟังอยู่แต่อาจจะรอให้มันอาจเป็นวิดีโอก่อนแล้วค่อยมาฟังก็ได้นะครับอีกอย่างหนึ่งก็คือ I am going to give out the PDF of all the PowerPoints in the lecture, so you don't need to take notes right away. You can just sit back, relax, and enjoy the presentation. Also, all right. So let's start with expansion. What we left off from last week.
I'm sorry,
Tuesday.
Professor. I have another question.
Yes,
I mean,
sure.
like, if you have like expansion, and then
Okay.
for example, like if now we just stop the third order, and then
Okay.
that third order is too complicated, can we expand the third order?
Okay.
You know what I mean?
No,
I mean, like you
don't-
first expand a generating function into
Okay.
like, for example, third order. And
Okay.
then that third order is too complicated to, for
Okay.
example, use the computer to compute. And then you
Mhm.
want to simplify the third order. Can you expand the third order, the third order term?
Okay. I think the answer. Okay, let me put my
Yeah, for
let
example,
me
like
put.
over here, you have like 1 plus r plus r square. So your r square
Okay.
is your second order. For example, if your r square is too complicated, can you expand the r square into another form?
Oh, okay. See, it is an idea. I don't know if you want to expand it.
Yeah, I'm not
You
sure.
have to
whether someone
expand.
gets-
Just say you have this, and you say r squared is too complicated, and you want to expand this into. Let me expand this, but the expansion need to be in different bases though. If you keep doing it the Taylor expansion, you're gonna get the same r square dependency. So you would have to expand r square into let's say Legendre polynomial or some Fourier series. Yes, you can expand it. I think it is an idea, but you need to use another basis of expansion, because if you use the same basis, you're gonna get back the r square.
I
I
see.
hope
Yeah.
I hope you know what I mean. Okay. All right. Where was I? I forgot. Oh, the expansion. Okay, let's open up the PowerPoint presentation on the expansion, which we left off from last week lecture. And we'll have time to start the next lecture, the solving by iteration. Okay, let me go to the slide where I left off. Perhaps I have this limit of expansion. Okay, now here I talked about the limitation of Fourier expansion, that the expansion only occur in periodic fashion มันจะต้องซ้ำเป็นคาบเรื่อยๆนะครับฟังก์ชันที่มันต่อเนื่องไปเรื่อยๆมันจะมีปัญหาเพราะว่ามันไม่ซ้ำกันนะครับแต่ว่าธรรมชาติของไซน์โคไซน์มันต้องซ้ำกันเพราะฉะนั้นมันจะต้องหลีกเลี่ยงไม่ได้ที่มันต้องเป็นคาบนะครับวิธีการแก้ก็คือว่าคุณต้องไปปรับการกระจายให้มันเป็นช่วงตั้งแต่เปลี่ยนจาก0ถึง2พายให้กลายเป็นตั้งแต่ลบถึงบวกอนันต์นะจึงจะสามารถทำได้แต่อันนี้ก็จะเป็นหัวข้อของการศึกษาเพิ่มเติมซึ่งน่าจะไม่ยากนะครับคุณไปเปิดดูมันก็จะมีสูตรให้คุณแค่นั้นเองนะครับแต่คอนเซปต์นั้นก็อันเดียวกัน so we have Taylor expansion that says that the accuracy is only good within this range of x less than 1. If x is bigger than 1, then the approximation is not good, because as you increase the power, the x becomes bigger and bigger and bigger. So this is not a good approximation if x is bigger than 1. If x is less than 1, it is very good because the big term, the high order term, is very small. It can be ignored. So that is the expansion. And I think we have this orthogonal, which we did. Okay, we have this orthogonal, and we began the Legendre polynomial, and over here. Okay, very good. Okay, so let me begin the story of the expansion with something that's more relaxing. It's not as intensive mathematics, but something more relaxed about a life of a scientist story. Okay, so when you are a scientist, you always hear this on the news that say, oh, you should read a paper every day. Okay, that's what's, I guess I saw this on Facebook, that you should read a paper every day. And so in my field of study, can I do that? I think that at least in my field of study, it is not possible to read a paper every day. Let me give you an example. Okay, I do research on the electrons and try to find the expression for the energy of the electrons, the formula for the electron energy. And so I have to read all kinds of physics paper. Let me show you one example of the paper that I have to read as my career as a scientist. So where is it? Over here. Okay, this is the. So here is a paper by the name of, how do I make it bigger? How do I increase the? There you go. Okay. Physical Review B. This is one of the very prestigious journal in physics. And I would need to read this paper about this exchange energy formula for the electrons. And look at this. Look at this paper and the content of the paper. A bunch of equations, that here and there, and a bunch of logic there, and all kinds of mathematics and the physics between. You cannot read this every day. You cannot even finish this paper in a day. Okay, for me at least. Let me show you a real life story of what I have to go through to do my research. It took me 4 months to read and understand this paper alone. And the reason it took me 4 months is because this equation here, okay, equation number 11 and number 12. And in this paper, it says when you take this equation number 11, you can rewrite this equation and becomes number 12. That is in the paper. In inverting this, we obtain as only one sentence in the paper, inverting this 11 into 12. Okay, and I was trying to derive this, just one line of paper. It took me 4 months to do that. And you would think that, why is that? It seems to be very simple algebra. มันเป็นคณิตศาสตร์ง่ายๆดีกว่าสมการ11มา12เนี่ยมันก็บวกลบคูณหารธรรมดาแล้วมันก็เขียนในนี้ว่าประโยคเดียวก็คือถอดรากออกมาแล้วก็ได้ตรงนี้นะครับแต่ว่าพอผมพยายามทำแล้วมันไม่ออกนะครับไม่มีทางออกนะครับและผมก็จะพยายามเล่าเรื่องให้คุณฟังว่าปกติเวลาเราทำงานวิจัยเนี่ยพอมันมีโมเมนต์แบบปิ๊งขึ้นมาเนี่ยเราหรือว่าโมเมนต์ที่แบบเราหาทางออกไม่เจอผมมีวิธีในการแก้โจทย์ยังไงนะครับเดี๋ยวมาดูกันว่าทำไมผมถึงว่าไอ้เบอร์11มา12เนี่ยนะครับมันเป็นไปไม่ได้ถ้าคิดตรงๆนะครับ so I'm going to show you why equation number 11 and 12 they're not the same equation if we work out the math. Okay, let me move this to my iPad. Okay, so to show you why number 11 cannot go into 12 or they are different equation, let me show you by making a simplification. Let's say we have here that the just to make it simple, let's say we set the rho equal to 1. Then we set kf equal to 1 and the rest. So number 11, equation number 11, when you look at this here on the left, you get this here. You say you get 1 is equal to, on the right hand side, 4, and then vk, and then kf is 1, so we ignore that in this example, and then 2 pi, the whole thing square. With the big parenthesis, what we have inside there is 1 minus 1 over 12, and then bk square. Okay, that's just the expression of the equation number 11 is saying. Now let's look at the what the equation number 12 is saying with this simplification over there, just to make it simple for you to see this example. So we have this on the left-hand side of the equation vk squared equal to 2 pi to the 4th power divided by 32. Kf down here is 1, just to make it simple for you. And then 1 minus 1/6 of k squared. The whole thing is multiplying to the row things here. That is 1 plus 1 squared. So we have this factor of 2 over there. You see, this author is telling me in his paper that you can simply, by simple algebra, go from number 11 to number 12. How could that even be possible? You see, if we do that, let me try to do that. Let I go from here. I can move this, all this here, the k dependent to the other side, so I get this vk is equal to, you move all this thing here to the other side, you have this constant, let's call that star constant, divided by 1 minus 112 and then k squared. So the k squared is inverse proportional to the vk. This is what equation number 11 is saying. But number 12, the k squared is on the top. 11 is down here in the denominator. And I was like, took me so many months to figure out why is that? What is the explanation? What is the explanation of this? Can anybody help me? Maybe you have a solution. Why is that? Equation number 11 and 12. This author says they're the same.
Is it because of the k is the vector? So basically, that's it's the inverse vector.
A good idea, but it's not the answer. So I thought about this. It's a hard problem. I thought about this, and one day I say, well, so I plot graph. I plot a graph of the vk from the equation number 11, and then I plot the graph of the vk from the equation number 12, and I saw that the graph are not the same. They don't agree. They're different expression at all. But only when k is very small do these two agree to each other. So then I found out that number 12 is not exactly as 11, but it is a Taylor expansion of the number 11, okay? And that is written in this paper, just one sentence, we obtain. We obtain, like so. An example would, I give you an example, like for example, you can expand 1 over 1 minus x, which in this case, x is downstairs in the denominator, and that can be approximately 1 plus x over here. You see, on the right-hand side, the x is upstairs in the numerator. On the left-hand side is down here, but it can be done using Taylor approximation. So the answer is that equation number 12 is not exactly the same as 11. They are Taylor expansion of one another.
ไม่เห็นกระดานนะคะ
Oh, there you go. Okay. Here. I was talking about the example of this expression, which you can expand this as Taylor expansion here. On the left, x is down there. On the right, x is up here. But they can be equal or almost the same because of Taylor expansion. the same concept as this one here. The K in the 11 equation is down there. Number 12 is up here. Okay, and it took me 4 months to unlock this secret with just one line of paper. So that's what my life is, and it took me so long to do my research, and I cannot read a paper every day because this is the paper in my field of research. Okay, I guess you can read that without going into detail, but I don't think that's important. That is useful. All right. So with that life story, I hope you relax a little bit from this วิชาการทั้งหลาย Okay. We'll finish up the expansion and go to a more exciting concept of solving by iteration. Okay. To sum up the expansion, I can write this here. Sorry, there. Okay. If we have a function f of x, we can always expand them into many pieces, and each piece is going to have the coefficient a0, a1, a2, the percentage of the mixture, these are a, and the bases, these are called bases, which are the function which we expand them into. They can be sine and cosine. This case will be Fourier basis. They can be a simple polynomial, that's a Taylor expansion, or Legendre polynomial, okay, the B. And by using the concept of orthogonality property, you can derive that the coefficient is this expression. Okay, we derived this in the previous class. That is the formula for the general expansion of any bases that are orthogonal in nature. So integrate them divided by the, down here we call it normalizing factor down there in this denominator. Okay, so I can show you how you do the Legendre polynomial, but you can do that at home by using Wolfram alpha to do this integration. What integration? This integration here. When I do that integration, I get this coefficient of the P0, of the P1, of the P2, and so forth. Okay, and I hope in this lecture you feel more familiar with this term, this approximation better. Okay. Now, if I plot the graph, I take this expansion, I plot the graph, I get this nice graph over here. The blue is the exact exponential function, and the green is that expansion up to 2 order of the expansion. Very good agreement. And if I look at each order and see how they are different from Taylor expansion, this is the first order of the Legendre expansion. The exact point is right here, not at 0. This is a 0 here, but the exact point is a little bit to the left, maybe minus 2 or something. If you add another term, the slope is similar to the exact function, but not precisely at the origin, but on average. If you add the third function, you have this curvature, very similar to the graph. So the concept is kind of very similar to Taylor expansion, okay? But on average, the value is the same on average, the slope is the same on average, and the curve is the same on average, not at any specific point, but on average, okay? And that's why when you look at the arrow profile of the Legendre expansion compared to the Taylor series, the Taylor is very good at the origin. You see that here is the error, and at the origin, the error is 0. But at some point, away from the origin, the error it increases a little bit and get very bad down there. But for Legendre polynomial, on average, they are the same over here. Okay, that's just the properties of that expansion. And of course, there are many properties that you can study, millions of properties. And this is just the example of one of those. Okay, so we have this homework problem. I don't know, you can try to do that to solve for the Fourier expansion. I can show you how to do this a little bit, since it'll be in your homework in the e-learning. Oh, by the way, the e-learning website of the Naresuan University is back online. So I'm gonna get back to the homework for 3 of you to do it maybe after this class. So let's do this example just to slow down a little bit. And I hope you can see this here of how you find the coefficient. Okay, let me put the formula for the coefficient. Any expansion that says f of x is equal to the summation of coefficient times any basis, let's call it Bn. Okay, if you do this, the question is, how do you figure out the value of the coefficient? And the answer is, you have this ratio at the top, you integrate f of x with the basis that we are talking about, and divided by the basis itself square. Okay, that is the formula for any expansion with orthogonal basis. Now let's focus ourselves to this digital pulse in this graph. That's just a signal in the digital. So if I do this, let's say my cosine basis, the A1. What is A1 in Fourier expansion? It comes from this expansion A1 and cosine of 1 times x. Okay, so the question is, what is the value of this here? Well, we look at the graph on the left. That is my f of x, and you notice that you can split the entire range into 2 regions. On the left is +1, on the right is -1. So we can then split the integration. In this case, let's go back here. Integrate, let's use my ink, is equal to integration of -1 to 0 dx plus another range is 0 to +1 dx. Okay. On the left range, the value of the f, in this case the f here, is +1, so we put +1 over there, and then times cosine x, integrate them. What about the toward the right? The value is -1, so we say f is -1 there in this range and multiply cosines of x, and you do the integration. And you can use that, use the software to do that. You can use your hand to do that. It doesn't really matter. You're gonna get the right answer anyway. So I hope you get 0.5 or something. I don't really know the exact answer. I'm just making it up. But I hope you get the idea. Okay. And this will be the end of the expansion. And I'm gonna get to the next chapter very quickly. We have about about 45 minutes or an hour, 45 minutes to cover, which is gonna be a short lecture on the solving by iteration. Okay. Any questions that you may have before we leave this expansion chapter behind? Anything? We have here our participant that we have here has reduced from 20 from last week to how many do we have so far? We have well, 5 or 6 participants. Very good. Very happy and appreciate your companion that stayed with me through this whole lecture. Okay, I'm waiting for the. What about you, Dishan? Are you doing all right before we go into the next?
Yes, Sajjan. Thank
Okay,
you.
all right. If there is no question just yet, let me close this PowerPoint and get to a more sophisticated practical advances of the material, namely solving by iteration. Okay. So let me turn off a closed expansion and change the slideshow to in the box. Okay, very good. All right. Let's have some. Where is it? Nice introduction music. Okay. So, one of the very important problems in mathematics is finding roots or แก้หารากของสมการ Okay. So the form of the equation is like this. You have on the left hand side f of x equal to 0, and then you ask what is the x that makes this equation true. So that is finding the roots of this expression. Now let me give you an example just to show you the practical problem in mathematics. The first one here, the f of x is x minus 1. What is the root? Well, it's very simple. It's x is equal to 1. What about this more complicated problem? Sine of x is equal to 0. What is the roots? In this case, the problem has many roots. You know, the sine x is 0. The x or the angle can be 0, pi, 2 pi, and 3 pi, or n pi. Any of these x will give sine x 0. So they are the answer of that equation. And how do you find the answer? What about you have a more complex polynomial, like in this equation here? Now this equation, the right-hand side is not 0, but minus x. But we can always rewrite this expression and make the right-hand side 0. How do we do that? We move this minus x to the left, and therefore the left-hand side will be this function equal to 0, so we get back the form of this simple function. So if you do the actual mathematics, you will get that the answer of this root is minus 8 and then 0. I hope you follow this. Seems to be very simple enough to do. What is that? And let me just slow down a little bit so I can show you the simple one. So we have this 1 over 8 x squared plus x equal to 0. What I do is I factor out x. X is outside. Now we have what is left inside. 1/8 x plus 1 equal to 0. And therefore, with that expression, x has to be either 0 or minus 8. You know, minus 8 come from this parenthesis. Okay, and 0 comes from this term outside. Okay, just to slow things down a little bit. All right, so this is the example. But how do you do it using a computer? Okay, you can plot graph. That's very simple to do. So you take this function f of x and then plot graph, and then you look at the graph. You know, use your eyes and look at it, and you say which location the graph is 0. You say it's right there on the left, it's right there on the right. So we have these 2 points That is x is 8, that's the root. Another one is x is 0, it's the root. So you can do this as well. But what about if you don't have a graph, or the problem is much more complicated, that you want to use some method to solve, to find the answer instead of looking at the graph ถ้าต้องการใช้เครื่องคอมในการแก้โจทย์เหล่านี้นะครับโดยไม่ต้องวาดกราฟโดยไม่ต้องแก้ด้วยมือเนี่ยจะทำอย่างไรนะครับ This is the topic of numerical method, the art of using computers to solve problems. So in this lecture we will look at 3 methods: the fixed point iteration method, Newton's method, and secant method. This Newton here is very surprising. Even in Newton's time, when there was no computers around, he still knows how to solve this problem. So Newton was very smart, a scientist who knows all kinds of things, not only mechanics, but also calculus, but also numerical methods. So he's a true genius of human civilization. So let's look at the fixed point iteration and how we do that to solve for any form of this fx is equal to 0. Okay. By the way, the research in fixed point mathematics is very blooming in Thailand. งานวิจัยเกี่ยวกับเรื่องของ fixed point ในประเทศไทยกำลังบูมมากนะครับถ้าเกิดคุณทราบเรื่องเหล่านี้ไว้เป็นพื้นฐานก็จะสะดวกในการที่จะไปเรียนต่อให้ลึกขึ้นในกลุ่มต่างๆที่อยู่ทั่วประเทศไทยนะครับ so how do we solve this fx zeros using this method called fixed point iteration? We begin by rewrite. So there are only three steps, very simple 3 steps, 1 2 3 ABC. So we rewrite this expression into this form. Okay, x is equal to gx. Let me give you an example. So we begin with this expression over here on the left, okay, equal to 0. And we say, we take this whole thing and then say x is equal to x plus f right here, over here. You see this is the same expression as before. If you cancel the x there and x there, you get the same expression back, and that's what I mean by rewriting the expression. So you rewrite this here into x is equal to something on the right, and we call that thing on the right g sub x. คือเราเปลี่ยนการเขียนสมการจากรูปปกติเนี่ยให้เป็นสมการแบบ x เท่ากับสักฟังก์ชันหนึ่งนะครับยกตัวอย่างเช่นผมมีตัวเดิมตรงนี้ก็เขียนแปลงได้แบบนี้นะครับซึ่งเป็นฟังก์ชันแบบเดิมถ้าผมหักล้างตัว x เนี่ยมันก็จะได้ตัวเดิมออกมานะครับแต่ว่าเราเขียนแบบนี้นั้นมีประโยชน์อย่างไร so what is the benefits of rewriting this here into this form? The benefit is that we can begin with the initial guess of the answer. Say we don't know what the answers are, so we begin with initial guess. Let's call that initial guess x0. Oh, let me guess. I don't know. Let's say minus 15 is my initial guess answer, and we can. By the way, we know that the answer are minus 8 and 0. Okay. เรากระซิบว่าค่าตรงๆก็คือลบ8กับ0นะครับแต่เราที่ต่างว่าไม่รู้ก็เลยเดาเป็นลบ15แทน okay so we have this initial guess. What do we do next? We take this initial guess and put that guess here into this g function. We will get back a new x. Let me show this in PowerPoint. Let's say we have this x 0 minus 15. You put this minus 15 back into the g here, you get new x value, some number, using that expression as g of the g. And you take this x1 and update it using the same g as before. You get x2, you get x3, and so forth. You have this series of iteration and you change the value from x0, the beginning, to the next, and the next, and the next. What happens? What happens? Let me give you an example of this iteration using that method. So if I use my minus 15, I put this into this expression of my GX definition. What I get is minus 1.87. I do this the same cycle. I take this x1 and put that into there. I get x3, x2. I get that minus 3. And keep doing it, x5, x6, x7, x8, x9. You see, the series keep converging to the answer of minus 8. Wow, that's very amazing how you can do this in a very simple way. Amazing. You can just keep updating, and it will get you this final answer of minus 8 there. Begin here. Okay, right there. I hope you understand this process. Even in English, there it's very simple. So we find a way to rewrite this function into this form, and how we do this is this by example. You take this f, and then you put this on the right hand side, and you make x equal to x plus the same f. You get this thing here, and you update the whole thing in cycle, and at the end it will converge to this minus 8. Now the question is, does it work all the time? I mean, is there a case where it does not work? วิธีการนี้มันใช้ได้ตลอดไหม มีบางอันไหนที่มันใช้ไม่ได้ หรือมันฟลุก หรือว่ามันเป็นยังไง มันมีสมบัติทางคณิตศาสตร์ที่บอกว่ามันเป็นจริงเสมอหรือเปล่านะครับ ถ้าเกิดไม่มีแสดงว่าอันเป็นบุญแต่กรรม ซึ่งก็ไม่เหมาะที่จะมาใช้ในการคำนวณ แต่ว่าถ้าเกิดมีนะครับ ถ้าเกิดมันมีทฤษฎีบททางคณิตศาสตร์ที่บอกว่าทำอย่างนี้แหละนะครับ สามารถมีคำตอบเสมอ อันนี้ก็พอลุ้นเอามาใช้นะครับ แต่ถ้าเกิดว่าได้แต่บุญแต่กรรมก็ไม่เหมาะนะครับ so does it always work all the time, this method of fixed point iteration? Okay, so before we go further, let me show you the Google code, the Google code to see. Now, last week there was this problem that the window was too narrowed. So let me change that here. To see the Google code, let me close all the window here. Okay, you can just go to the one-stop website and then click on the number 2 here. Okay, solving by iteration. Let me go to the new tab. This is the Google code. Let me adjust here. There you go, and maybe adjust the size to make it better. Okay, now there are explanations. Let's go to the fixed point iteration program. Okay, here's what I got from the output. Remember to click on the play button here. I click there, and the first time you click, it's gonna take a little bit of time, but now you should be okay. Okay, so let me take you to all this code. This is the output. You see there, minus 15, and then you update the function. It changes to the answer, minus 8. Okay, so this is the structure of the Python code. In the beginning, I have to import the math library. This will take care of the function, cosine, exponential function, and all the strange function is inside the math library. So you have to import it. In here, I defined my f function. Okay, f is x squared over 8 plus x. This is my fx, which I want to solve or to find the roots. And the rest is just to give you the updating. This, let me show you a little bigger. This is the updating code. See here, on right hand side is my g function. The g is x plus f. Let me go back to the PowerPoint and to show you what the g is. Here's my g. G is the x plus my choice of f. That's my g. And I keep updating it. And by updating, I mean the x of the next step, the x of the I plus 1 is equal to the function of the previous step, like so over here. So I do this updating many times. I get that answer. I can change the initial guess. Let me do that. Let me change my initial guess from minus 15 to minus, let's say, 13. And I click play, and it takes up a while. And at the end, you see, it changed the value and then converts to minus 8 at the end. Takes only 6 iterations to get the accuracy up to 8 decimal places แม่นยำถึง8ตำแหน่งทศนิยมต้องใช้6การคำนวณ6รอบด้วยกัน Okay, so let me get back to yes, someone asked questions.
Yes, I just wondering that the number that we choose for the initial value, it should be important because of as you shown the example, the root of this this course is like a 2 numbers, but we
Okay.
just only choose one initial number. That
Good.
should not write in this
Good.
case.
So we have some of the complicated functions. We have many roots, and TK is wondering if we choose different initial guess, would we get the different final answer, the 0? And the answer is not easy, but I can show you right now here. But let me change the way I run this Python code, because I'm going to make many changes as I show you in the lecture. But I don't want to save that change. I have to go to, let's say, open in playground mode. And this will not save the things that you do the changes automatically. Okay, let's get back here. Now, suppose I want to get, now,ในงานจริงๆเราไม่ทราบคำตอบคืออะไร แต่สมมุติว่าเพื่อการศึกษาเรารู้ว่าคำตอบมันมีเลข0ด้วย เราก็จะลองทิศทางว่าเราจะเปลี่ยนค่าเริ่มต้นให้เป็นใกล้ๆ0นะครับแล้วดูว่ามันจะพาเราไปที่เลข0ได้หรือเปล่านะครับ so let's say we don't know the answer. Let's see if we can get ourselves to the 0 roots. Okay, maybe I get this 0.5 as the initial guess, and then rerun the code. Tick tock, tick tock, tick tock. Initializing connected. Oh, the method does not work in this case. Why is that? It blows up to infinity. My God. Okay, maybe I'm just bad luck. Let me change to 0.5. Like so, and then rerun the code. Okay, now we are cheating. Now กำลังโกง what do we get? Not the answer. We can never get to the 0 roots in this case. So we give you the wrong answer. There's no convergence for this solution for this here, and that becomes very bad problem. I mean, you cannot have a math structure that gives you the answer one day or one case, but does not work in some other case. You want something that always work all the time. So this is not a good method. It's not a good method at all. Okay, very good questions. But there's a way to fix it. Okay, there's a way to fix it. That's where Newton's method comes in. Okay, let's get back to the code. There it goes. You rerun the things here in your Python code. Okay. Now, the fixed point research, what does fixed point means in this case? Okay, you hear this all the time in Facebook, in one of the research that they do in Bangkok University, in Konkan University, you have this fixed point research group. What are they? What does fixed point means in mathematics? Notice here when the things converges to the final answer. If I use my input as -8, put it over there, -8, I get back as output the same value. If the input is the same as the output, that is what we call fixed point. The point that does not change anymore in the mathematical structure. That's what fixed point means. Okay. Anyway, that's just the definition. Let's do some quick quiz. Okay. To see if we can. We did this with this already, and then we answer thanks to the question from the audience. We found out that this method does not give you the x0 solution. It does not work in this case. What about if we want to modify the function f to be the sine function? What do you do? What do you do? Okay. Before I do this, let me, since we have seen this case of x0, let me show you another way of constructing the g's of x, okay, and see how that would change the answer. Okay, there is also a very good mathematical theorem here to be learned in this case. So we begin with the function of f of x. For example, x squared over 8 plus x. This is my f, and I want to construct my g such that this equation is true. And, let me erase this. Okay, so what do I do? I say that x is equal to x plus f of x. Okay, that's my g. I can define my g this way. This is my gx that I define. Okay. There's another way to define g's of x, which is also valid, the same function. I can say x is equal to x minus f of x. Is that okay? It's also okay, right? Why? Because if I cancel this x here and there, you get back 0 is equal to f of x. If I do that, so this expression of g is perfectly valid. I can define this. This is my g instead. I use minus instead of the plus sign. Okay, so let's go back and change the Python code and study the behavior. You know, imagine that you are a researcher and you don't know all of this, and you're trying to find a way, trying to study the answer, and you have this idea. Oh, I have this idea. Maybe I can define my g this way. Let's see what happens if I define my g this way. Okay, so I go to the Python code of Ajahn Teepanis, and I say that this is my g. Okay, it's my g. Where do I define my g? There you go. I change this from x plus to x minus f of x. Let's do that. Let's do that. And I use the initial guess as 15 as before, and I do this. I say click play. What do I get? There you go. Now I can never get to minus 15 anymore. Let's say maybe I'm just bad luck. Let me change it to minus 13. 13 as my initial guess, and then click play. With this new way of defining g, I click play, and I never get to minus 15 anymore. It's gone. Oh, maybe if I change this to something very small, like 0.5. Would I do this here? and I do this play again to see what I get. Initial guess is minus 0.5. There you go. Now I can get to this answer of 0 just by changing the g value. I get to another solution of the root. I get to 0. If I change it to minus to maybe 1.7, 1.7, that's my initial guess. Let's do that. I get very good. I'm happy now. Now I know how to fix my method so it converges to another solution, which is 0 in this case. Now there is a theorem, the exact math theorem that tells you why this is the case. Okay, we'll see this in the middle of the lecture. Okay, so let me change it back to plus. Okay, now what was the question again? The first quiz, I forgot. What was the first quiz? Quiz number 1. We are supposed to change the f function, right? To what function?
Cos x.
It's sine and cosine. I forgot. Let's see. Oh, sine of x. Now we are changing the sign, the function to sine of x. So what do? I simply just redefine my Python definition of my f of x here, and I return my. If I do this, it will not work because the Python does not know the sine function. If I click that, does it work? See, it's red here. It says error, and it says name sin is not defined. It does not know sin. Does not know sine. So what I do is I have to import the math library or the math routine here, and then use the math object instead. So the sine function is defined inside the math object. So I do this, and then I need to change my initial guess. Let's say, what is my initial guess? Let's say I say 0.5 as my initial guess. I run the code. What do I get? Oh, there it goes from 0.5 to something to at the end 3.14. So what is 3.14? Let's ask Patharada there to แก้ตัวจากโจทย์ข้อที่แล้ว 3.14 คืออะไร
Pi ค่ะ
very good. Okay. All right. Now turn on your camera so I can see your smile for this right answer. Okay, thank you. Now you get to the pi, and from the PowerPoint, thank you, the PowerPoint presentation, that the answer is pi, or 2 pi, or 3 pi, or 0. But as you might guess, and TK will guess, that you can never get to the 0 solution because of this definition of G. Okay, let me show you this. If I start my initial guess as almost 0, like this, and rerun the expression, you never get to 0. You keep deviating from 0 to get some number. So there is this problem with this method. Sometimes it works, sometimes it doesn't, but there is a theory that tells you when that works and when it does not work. Okay, but let me get back to the minus 15 before we go to the PowerPoint presentation over here. I forgot what was that. Must be x squared divided by 8 and plus x over here. Okay, let's check if I get it right. 15 to 8. Very good. So I hope you sort of understand the basic working of this initial method of iteration. Okay, so sometimes it doesn't work. Newton was a genius of his time, even in this human history. because he knows a lot about so many things. Like Euler. Euler is also a genius. In every field of math, you see this Euler's identity. So Newton's method, he proposed another way of constructing the updating function. Let me call this g an updating function. Why? Because we use g to update the x from x0 to x1. Put into g, you get new ones, and so forth. So g is an updating function. He changed the way we define g from the previously into this form, x minus fx divided by x prime. This is the derivative of the x function. So the function f has to be well defined. We have to know how to compute the diff of the f to get f prime. Let's see how this thing works. Okay, before we get to the properties. We have this function f. That's my f. I then compute my f prime. You know how to do this. You take the derivative, you get x squared. You take number 2 down here, you get 1/4 instead. What about this x here? You get +1. So we have x prime there. And we build my updating function. Okay, g is x as before minus f divided by f prime. So we have this new Newton's formula of the updating function. Very good. So let's see how it performs. This is the series of the Newton's updating function using this my g. This was the previous fixed point iteration. Okay. Now you know for Newton, it takes only 4 or 5 iterations to get to the answer up good to 8 decimal places. As for the fixed point iteration, it took longer, much longer here before you get to the very precise answer. So Newton's method is faster in this case. Let's change that. Let's do the same thing, okay, with Newton's method and see if we can get ourselves to the 0 answer for the Newton's method. Okay, let's get back to the code over here. All right. This Google Colab has many sections. If you click on this list of table on the left panel, click there. You see all the sections that I have for you. You can go to the Newton method below, right there. So in this method, you have this explanation and so forth, and at the end, the code. The code is the same, except that the updating routine is different. In this case, my updating is x minus f divided by the f prime. This is my definition of f prime. So to do this Newton's method, you have to define 2 things. You need to define the f in this case and define the f prime in this case. And so you can imagine that there are some applications, some other job, something that you cannot compute f prime. How is that? For example, you want to study stock markets. In stock market, you only have dots and points in the data and information. You don't have the actual function. So you cannot compute the derivative in this case, okay? And that will be the next secant method. But in this case, suppose you know how to compute the fx. And this is my case of my fx. I do the f prime and get that here. So with that, let's see how it performs. Right there, initial guess is 15. You get to -8. Let's check with the TK's question. Let's say if I begin by chance 0.5 as my initial guess, what do I get? Very good. Now Newton's method gets you to this answer of 0. Oh, interesting. Now let me change my function to sine function. let's say I simply need to define my fx here. Math is sine of x right there. So what would be the derivative of sine x? Let's ask Dchen. So Dchen, what is the f prime in this case? Just to give me a chance to. Are you there?
Oh, cos x. Yes, Ajahn. Hello.
So what is the derivative of f prime? Oh, I'm sorry. What is what is f prime? Cosine function. Okay, very good. So we have math and cosine function right there. So we are all set with the Newton's method. Let's change the my initial guess is 0.5. Do the calculation. You get 0. What if I change my initial guess to something bigger? Let's say number 3.0. What do I get? I get pi. You see, it took only 2 iterations. You see here, very fast. Only 2 iterations to get to the final answer. Now, you can imagine. You have heard somewhere on the news that you can compute the pi value up to million decimal places. Now this is the way you can do it. You take you only 2 iterations to get to 8 decimal places of the pi value. What if I get to the like 6, a 6 here, a bigger number? There you go. I get to 2 pi. So Newton's method, because of his genius, we have this method that can get you to all the solution you have in the mathematical structure. Okay, always work. It always works, except just one exception. Can anybody tell me what that exception is? Newton always works. Yes.
I think it's like we have to choose the right initial function. That is the flaw on this method.
Okay. So if that's one inconvenience. So if you choose the wrong, if you choose the bad initial condition, it takes longer to get the answer. But at least you get the answer. But there is one case where you can never get the answer from Newton's method, and you can see that from here. Let me get back to the PowerPoint so you may see the problem of his genius there. This is a formula for Newton's method. Okay, you're updating. But there's something, and it does not happen very often. มันเกิดขึ้นไม่บ่อยนะเกิดขึ้นนานๆจะมีทีนะครับซึ่งเป็นการฟลุกแต่มันมีเคสที่ไม่สามารถหาคำตอบได้โดยใช้กลวิธีทางนิวตันอันนั้นคืออะไร
divide by 0 หรือเปล่าครับ
Very good. Okay, let me give you an applause there. Okay. Now it is too bad that you are born in this century, and if you were born in maybe 17th century, you will be it'll be a TK Skywalker's method series. Okay, very good. So in some rare condition, if the f prime is 0 at the solution, then this Newton cannot give you the answer. That is one. So in this case, what do? If you are so unlucky to have that solution, to have that condition where the f prime is 0 at that solution, what do? You use fixed point instead. So that's why you need to perform your calculation using many methods. It does not mean that you have this Newton, you say it's good, so let's do only Newton. No, you have to do many methods and compare them just to make sure. Okay, so I hope by now you will sort of have a basic function of the Newton method. The secant method will be in the next slide, next lecture, because we are out of time. But before we go to the secant lecture in the next lecture, let me give you this quiz. And this quiz is going to be very good for here. Where's my quiz there? Okay. Now, okay, let's think about this as your homework problem. I'm not going to give you the solution, but let's imagine that you are a researcher and you want to practice doing research. Let's do question number 2. Suppose you want to compute square root of 2 there, using only a simple operation like plus, minus, adding, subtracting, multiply, and division. Why do you do that? Because in the actual CPU of the computers, you can only do simple calculation, the plus and the minus and multiplication and division. But somehow, from these simple things, you can make another advanced function like square roots, exponential, and so forth. One of the example of this Newton's method is how do you devise a method to find square root of something using only plus and minus, and then and so forth. Okay, so that's will be the quiz, just to practice your understanding, and we'll get back to the finding roots in the next Tuesday. So any questions so far? I hope that this lecture feels better somehow, and I think the reason is that you sort of have developed a very good listening skill in English so far. Okay, so ตอนที่ผมไปเรียนที่อเมริกาก็ใช้เวลาประมาณหลายปี6 เดือนนี่สามารถจะสั่งข้าวสั่งน้ำได้แล้วก็ใช้เวลาประมาณ1 ปีเนี่ย1 ปีนี่จะสามารถที่จะขอเบอร์โทรสาวได้แล้วนะครับโดยขอเบอร์โทรสาวได้แล้วก็แต่ปีครึ่งน่าจะเริ่มพูดโจ๊กได้พูดให้คนหัวเราะได้ปีครึ่งพูดให้คนหัวเราะได้พูดให้คนซาบซึ้งอะไรต่างๆนี่คือเริ่มสามารถที่จะสร้างอารมณ์ได้นะครับแต่ปีเดียวเนี่ยใช้เวลาสามารถจะมีความเนียนในการขอเบอร์โทรได้แล้วนะครับเพราะฉะนั้นคุณสามารถจะฟังและเข้าใจใช้เวลาเพียงแค่เลคเชอร์เดียวถือว่าเก่งมากๆนะครับแสดงว่ามีพื้นฐานคล่องมากๆโอเค so any question that you want to ask before we leave today for this lecture? Anything you want to add?
Yes, I would like it. How can I say? It's like, can you guide us or give us more keyword to understand or to learn more about the phenomenon of the fixed point method?
Oh, okay. You want to know the fixed point method?
Yes,
very
because
good. Let's go back to the slide. Okay, a fixed point method. I shouldn't show you this. Okay, because it will not be fun. The fixed point method concerns about how you solve, how you find a solution, so that at the end you get back this fixed point condition. Okay. This what I'm showing you here is a fixed point condition. Like keep going. This is what we call a fixed point condition here. But to get to the -8, you have many methods that you can do. You can use this simple updating function, x plus f. You can use x minus f. You can use Newton's form of x plus f minus divided by f prime. So this research has to do with how you define the g function and get you the answer as fast as possible. Now in quantum mechanics, okay, I can give you some keywords. In quantum mechanics, we solve this problem using iteration. And let me use my but where is my iPad screen? Okay, over here. That's how you see it. In quantum mechanics, you have to solve problem using iteration also. And when you do that many times, you have x2, x3, and so forth, the solution oscillates between two values and it can never get to the final answer. For example, if I have this x0 as -5, the x1 will go to -7. The next one will be -9, and the next one will be -8.5, and the one will be -7. You know, it oscillates up and down. It can never get to -8. It just keeps changing. So this is in quantum mechanics, and you need to know how to deal with new updating function. Okay, and that's the fixed point research. I guess there is what is the name of that person who solved this, who find a way to solve this oscillating. I know that. I knew that. I forgot. Okay. So I hope I don't know, but I'm not an expert in fixed point. I just know in the very basic things about fixed point. I can show you the expert though I think he's a professor in Bangkok University. It's only one professor in mathematics in Bangkok University. You go search for that, and you should give him an email and ask him more questions. Yes, Miss Hathaithip, turn on her microphone and you want to say something. Any comments? Do you think this lecture is better in terms of the screen? Can you see it clearer? Are you happier with this lecture? Or some any other comments you want to add? Yes, I see this.
ค่ะจะถามว่าไอ้ตรง x ที่อาจารย์เลือกโชว์อะค่ะว่าแบบถ้าเป็นอะไรที่ซับซ้อนกว่านี้เราจะต้องเลือกโชว์ x ที่มากกว่า8ตัวไหมคะแล้วมันถึงจะเข้าใกล้ค่าที่ถูกต้อง
โอเคมันปกติอย่างเช่นถ้าเป็นการแก้สมการควอนตัมจะใช้ประมาณ 30-40 รอบครับกว่าจะตอบคำถามได้โดยเฉพาะถ้าเป็นกรณีที่มันยากๆมันก็จะลู่เข้าช้ามากๆบางทีมันไม่ลู่เข้าเลยก็มีนะครับเป็นร้อยเป็นพันก็มีนะครับถ้าเป็นการแก้สมการควอนตัมนะครับถ้าใช้ซึ่งสมการควอนตัมฟังก์ชัน f มันจะยุ่งกว่านี้แต่ว่ามันจะมีคอนเซปต์เดียวกันนะครับโดยพื้นฐานเข้าก็เหมือนกัน so Hathaithip was asking if we need more than 9 iterations to find the answer, and the answer was yes. Sometimes if the problem is difficult, it can take many more iterations to solve for the answer. Okay. ก็บางทีก็ขึ้นอยู่กับจำนวนขึ้นอยู่กับความแม่นยำที่คุณต้องการใช้ด้วยนะครับถ้าคุณต้องการคำตอบแบบหยาบๆคุณก็อาจจะเซตค่า cut off หรือค่า threshold นะครับว่าถ้าเกิดค่ามันไม่เปลี่ยนแล้วก็ให้หยุดเช่นสมมติว่าคุณเซต threshold ว่าถ้าค่ามันเปลี่ยนต่ำกว่าจุด1หรือว่าเจอคำตอบแล้วนะครับก็อาจจะเจอที่ตรงนี้นะครับที่เบอร์6เนี่ยที่เมาส์ชี้อยู่เนี่ยจากเบอร์5มา6เนี่ยคำตอบมันเปลี่ยนไม่เกินจุด1ก็หยุดการคำนวณก็บอกว่าก็รายงานผลเป็นจุด79984ประมาณนี้ขึ้นอยู่กับว่างานของคุณ ต้องการที่จะใช้พลังงานหรือต้องการได้คำตอบละเอียดขนาดไหนแม่นยำแค่ไหนนะครับถ้าต้องการใช้ละเอียดมากก็ต้องรันนานๆก็จะเสียเวลานานขึ้นตามปกติ
ค่ะ
นั่นหมายความว่าเราสามารถที่จะเลือกสปีดที่จะ convert to fixed point ได้ถูกต้องใช่ไหมครับอาจารย์ว่าจะเพราะว่าบางปัญหานี่เหมือนกับว่ามันจะ convert ช้ามากๆจนจนเดลต้าการเปลี่ยนแปลงมันน้อยมาก
ๆครับผมเราสามารถจะเลือก accuracy ได้ว่ามันจะให้ลูกเข้าเนี่ยมันจะเปลี่ยนกี่เปอร์เซ็นต์ถึงจะถือว่าพอเปลี่ยนได้ถ้าเปลี่ยนปั๊บก็จะทำให้โปรแกรมมันหยุดทำงานหรือว่ามันทำงานครบเนี่ยช้าลงหรือว่าเร็วขึ้นตามที่เราแก้นะครับ so we can change the cut off the percentage of which the x changes we can change that and it will affect the accuracy of the iteration. Okay, so I'm guessing we are at the end of the lecture number 2, and I'm very happy that you are happy. I'll see you again. We have PDF of the PowerPoint. We have the video recorded. You can come back and see it later in case you want to review. If there is no other questions, I want to give you an applause for being with me and the theme song to all right, I'll see you next Tuesday.
Thank you so much, Ajahn.
Thank you.
thank you
ขอบคุณค่ะสวัสดีค่ะ
ครับ
สวัสดี
ขอบ
ครั
คุณครับ บอาจารย์ thank you professor
ครับผม
ครับผม